Hi everyone, my name is Jessica Blow. I'm presenting my 2-year project on F127DMA as a smart liquid embolic agent for dynamic adjustments to brain aneurysm, embolization, and healing. Brain aneurysms are weaknesses in the cranial blood vessels that bulge out and fill with blood. They're a serious condition, with mortality rates as high as 40%. Approximately 6.5 million Americans suffer from an unruptured brain aneurysm. But because these brain aneurysms are subject to constant blood flow in the carotid artery, they're prone to ruptures, causing hemorrhagic strokes, and approximately 30,000 suffer from ruptures annually. Currently, intrasaccular coiling is the most prominent technique to treat brain aneurysms, but due to their inability to biodegrade and their permanence, they can often lead to drawbacks such as incomplete occlusion, thrombosis, edema, and hydrocephalus in 20 to 30% of cases. Emerging liquid embolic agents, or LEAs, offer advantages in terms of price, time, and efficacy, but they also currently suffer from drawbacks such as mass effect symptoms and high thrombogenicity. Thus, there exists an urgent need for improved brain aneurysm therapies. The goal of this project is to develop an enhanced, innovative, intrasaccular LEA for brain aneurysm treatment. By combining multiple biocompatible components, I hope to create a modern hydrogel therapy with improved outcomes and fewer drawbacks. This project solution to curing aneurysm is introducing an LEA that's injectable through a catheter into an aneurysm. It's observable under X-ray. It is stable for an extended period of time, which allows for healing. It's cell adhesive so that once the aneurysm is occluded, the body's natural wound healing process can occur and biodegraded after the wound healing process takes place. The base of the gel is F127DMA, and it's dissolved in deionized water as well as iohexyl. Iohexyl is the radiopaque agent that allows the injection to be visualized, and then FDMA must be chemically cross-linked because chemically cross-linking it gives it the strength and stability it needs to retain inside the aneurysm. And in order for this chemical cross-linking to occur, there must be a catalyst used, and this catalyst is comprised of ammonium persulfate, iron 2 chloride, and ascorbic acid. FDMA was synthesized in the lab by reacting pluronic F127 with methacrylate ends and then cross-linking them with free radical polymerization at 37 degrees Celsius using a redox system. Radiological testing and specifically single-frequency time sweeps were conducted to determine injection parameters and verify gel stability. To test for cell adhesion in blood-like conditions, cubic cells were plated onto cross-linked FDMA in a 4 mg per milliliter fibrinogen solution. DSC was also run to verify the reverse thermoresponsive nature and the phase transitions of FDMA. Silicon mold experiments were run with the gel inside a silicon mold under water flow from a peristaltic pump of 5 cc's per second, which is the cerebrospinal fluid rate, to determine long-term stability of the gel. The setup for the silicon model aneurysms is in the next slide. And regarding animal experiments, because swine injections require advanced clearance, I did not personally conduct them, but my mentor was the hands behind my experiment. However, in terms of the procedure, the animal was sedated and then the gel was injected under angiography. So here's a setup for how I injected the gel into the silicon model aneurysm. Injections were imaged via angiography and the use of the radiopaque agent iohexyl, and injections simulated real patient conditions. So the system was filled with DI water that was maintained at 37 degrees Celsius to simulate body temperature, and it had a peristaltic flow rate of 5 cc's per second to simulate cerebrospinal fluid. And then during injection, the gels were drawn into a syringe and then were injected via a soft food microcatheter into the silicon model aneurysm. And then immediately after injection, a balloon was inflated inside the parent vessel for 120 seconds to prevent leakage of the gel from the aneurysm. So first, I'll talk about injectability and observability. Last year, I designed a surface model of an aneurysm in CAD via Autodesk Fusion 360, and I continually use this model to print out silicon aneurysms to test and inject on. My DSC data also confirmed the RTR properties and the phase transition of FDMA. I conducted successful injections into a silicon model aneurysm, so I showed that it was injectable into the silicon model aneurysm as well as observable. This year, as you can see in figures 12A and 12B, I injected into a swine, and you can also see that the gel successfully occluded the artery, meaning that it's injectable, and you can see the injection. So the gel is observable under injection in an in vivo model. Also, you can see in figure 13 that in rheology, 66 milligrams of iodine per milliliter, the results did not differ significantly from 0 milligrams of iohexyl per milliliter, meaning that the presence of the contrast agent does not significantly affect the cross-linking ability of the FDMA. So therefore, the gel is injectable in vivo models, and it's observable, and the contrast agent does not interfere with the injection. For acute and long-term stability, last year there wasn't much done. It was just an injection into the silicon model aneurysm, and it lasted for 13 days. This year there has been a lot more done, and as you see in figure 14, that's data from a rheological test. And in the first blue box, you can see that the gel, it has a low viscosity at low temperatures. This is why it's easily injectable. And then you see in the second blue box that as temperature increases, the modulus increases exponentially, and this forms the micelle, or the physical gel. And this is what gives the gel its acute stability, which means that it's able to instantly occlude the aneurysm. But this micelle gel is still relatively weak and would wash out pretty quickly. But then with increased time and temperature, the gel, as you can see in the third blue box, does chemically cross-link, and this gives it the long-term stability it needs to last inside the aneurysm for an extended period of time, like 6 months. So another test that verifies that the gel has long-term stability is the silicon mold experiments. And as you can see in the graph, the gel's modulus stays relatively constant. The reason it doesn't hover around 100% is because not all of the dimethylcrylate ends are completely cross-linked, but once these dimethylcrylate ends are completely cross-linked, the gel is even more stable, and it does hover around that 100%. In figure 16A and 16B, you see that the LEA successfully occludes the aneurysm from blood flow, which prevents future ruptures. And in figure 17, you see that the LEA retains inside the aneurysm for 7 weeks. So therefore, the silicon mold experiments, rheology, and the injections into the silicon aneurysms, they prove that the F127 DMA gel has acute and long-term stability. As it relates to cell adhesion, last year I found that uncross-linked F127 is non-cell adhesive, and cross-linked F127 DMA alone is minorly cell adhesive. This year, when I plated cubic cells with cross-linked F127 DMA in a fibrinogen solution to simulate more blood-like in vivo conditions, I found that cells adhere to the substrate well, and they form major cell-to-cell connections, as you see in figure 18, which means that fibrinogen helps the cells adhere to the gel. The beginning of angiogenesis is also observed, showing that cross-linking actually promotes protein adhesion, which helps endothelial cells migrate to the gel, which helps the aneurysm heal, and it heals the overall deformity. That's because there's endothelial cell adhesion and migration. The gel facilitates the body's natural wound healing process. In conclusion, I took the first steps for the optimization of the treatment of cerebral aneurysms by creating a thermoreversible cross-linkable polymer gel. This biocompatible gel cross-links inside the aneurysm, which effectively occludes the aneurysm and allows the treatment to withstand shear and blood flow. Opposed to existing therapies, iohexyl is a safe contrast agent. The gel is also easily injected through any microcatheter, and there's a short procedure time because it's a single injection. I also conducted successful X-ray guided injections into 3D printed model aneurysms and an in vivo SWAD model based on rheological measurements, and I observed that incubation with fibrinogen enabled the migration and adhesion of cubic cells onto the gel surface. So because the gel conforms to the aneurysm, works with the wound healing process, and enzymatically biodegrades, it's a patient-specific therapy. It's also applicable to several other vascular diseases such as peripheral and visceral aneurysms and arteriovenous malformations. While metallic coils have been the predominant therapy for brain aneurysms for the past 3 decades, the future paradigm of treatment will involve polymer-based solutions that accelerate curative remodeling of the disease via molecular/pharmaceutical actions. This bioengineered polymer takes the first steps towards the paradigm shift. A limitation is that the DMA ends of FDMA sometimes does not completely cross-link due to changes in pH or temperature, so you have to be careful with storage and frequently test whether it's completely cross-linked. In the future, I hope to optimize occlusion time so that the gel retains inside the aneurysm for 6 months. I will also ensure the DMA ends are completely end capped. I also hope to inject the LEA into smaller catheters to increase precision. Cheaper catheters that were used have larger diameters, which breaks the chemical bonds of FDMA, causing a lower retention time inside the aneurysm. In the future, more precise catheters will be used. A biodegradable oligopeptide will also be inserted. While the exact peptide is patent pending, so I can't completely disclose everything, the basic mechanism is that it will allow the gel to be degraded by enzymes in the blood. These changes will allow me to take the next steps towards a personalized, transformative treatment for brain aneurysms.